Hello everyone, my name is Ramachandra Hegde. I am student of Anjuman Institute of Technology and Management. I am pursuing my computer science degree and currently I am in final semester of my UG program. Today I am going to present a seminar on analysis of facial emotion recognition under guidance of Professor Syed Noorian. So without further ado, let's get to it. In this seminar, initially we will be introduced on what emotions are and what are their importance to us. Then we will be overlooking various data sets which are used to train the machine learning models. In the later part, we will understand various machine learning and deep learning algorithms applied here and also compare their accuracy and error rates. Finally, after understanding all this, we will be drawing an inference. To offer solution to any problem, understanding thoroughly about it is very important. So, before diving into the realm of facial emotion recognition, let's understand what emotions are and also the importance of facial expressions in communication. Emotions are psychological states brought by neurophysiological changes variously associated with thoughts, feelings, behavioral responses, and degree of pleasure or displeasure. Emotions are often intertwined with mood, temperament, personality, disposition, creativity, and motivation. Emotions play an important role in our daily lives. Each and every day, we spend a tremendous amount of time witnessing emotions of others, interpreting what these signals might mean, and determining how to respond to each one of them and deal with our own complex emotional experience. We need to understand why this is such a complex process. To know this, first we should know how emotions are expressed. First way is very easy. It is by verbally expressing one's emotion in the conversation. Second one is way more complex than what it seems. Emotions are expressed through our thousands of nonverbal cues and behaviors. This includes postures, facial expression, eye gaze, and gestures, and many more. These are influenced mostly by our subconscious mind. These collectively form nonverbal expressions of emotions. Nonverbal communication plays an important role in how we convey meaning and information to others, as well as how we interpret the actions of those around us. What a person actually says, along with his or her expression, appearance, and tone of voice, might tell you a great deal about what the person is really trying to say. According to scientific studies, humans rely a lot on nonverbal methods of communication. While verbal methods of communication may be primarily used, a lot can be derived from persons' nonverbal communication. Statistically, nonverbal forms of communication make up about 60 to 70% of total communication. While we are at it, one of the major cues in nonverbal form of communication is facial expression. Consider how much information can be conveyed with a smile or a frown. The look on a person's face is often the first thing we see even before we hear what they have to say. While nonverbal forms of communication and behavior can vary dramatically between cultures, the facial expressions for happiness, sadness, anger, and fear are similar throughout the world. Facial expressions are possible because of one or more motions or positions of muscles beneath the face. These movements convey emotional state of individual to observers. Let's now know about types of facial emotions. Basically, there are 6 types of facial emotions. Those are happiness, sadness, fear, disgust, surprise, and anger. In addition to these 6 basic emotions, there are 21 compound facial emotions more. Let me illustrate what is a compound emotions through an example. Facial emotions of happily surprised is very different from angrily surprised. Even if they fall under same category of basic emotions, these two emotions are poles apart from each other. Till now, we have learnt what are emotions, what are types of communication, how nonverbal communication is different from simple verbal communication, and importance of facial expression in nonverbal communication. Now we will find out importance of facial emotion recognition. Nowadays, more and more machines are evolving, and for this evolution, they need to improve their interactions with humans. As we know how much important these emotional expressions are, it is inevitable for machines to implement facial emotion recognition for better performance and results. Consider a scenario in which system detects drowsiness of a driver in the car and if detected causes the alarm and stops the car. Or a scenario where psychologists using this system to detect what their client might be feeling so that diagnosis might be done better. Facial expressions are more explanatory in situations where words fail, like a shock or a surprise. Moreover, lying through words is more difficult to detect rather than detecting emotions. Thus, it is essential to study, use, and analyze facial expressions. Let's now see which are all the data sets used for facial emotion recognition system. Datasets are collection of instances that all share a common attribute. It is a collection of related sets of information that is composed of separate elements but can be manipulated as a unit by a computer. For machine learning models to understand how to perform various actions, training datasets must be first fed into machine learning algorithm, followed by validation datasets to ensure that the model is interpreting this data accurately. Once this training and validation sets are fed into the system, subsequent datasets can then be used to sculpt the machine learning model going forward. The more data you provide to the machine learning system, the faster the model can learn and improve. Different datasets used in training and validation of machine learning models are as follows: Extended Concatenate dataset, Japanese female facial expression dataset, Facial emotion recognition 2013 dataset, Acted facial expression in the wild dataset, and Emotionnet dataset. The extended concatenate dataset contains 593 video sequences from a total of 123 different subjects, ranging from 18 to 50 years of age with variety of genders and heritage. Each video shows facial shift from neutral expression to a targeted peak expression, recorded at 30 frames per second with a resolution of either 640 by 490 or 640 by 480 pixels. Out of these videos, 327 videos are labeled with one of 7 expression classes: anger, contempt, disgust, fear, happiness, sadness, and surprise. It is widely regarded as most extensively used lab controlled facial expression classification database available and used in majority of facial expression classification methods. The Japanese female facial expression dataset consists of 219 images of different facial expression from 10 different Japanese female subjects. Each subject was asked to do 7 facial expressions, of which 6 are basic and a neutral facial expression, and images were annotated with average semantic ratings on each facial expression by 60 annotators. Facial Emotion Recognition 2013 dataset was created during ICML 2013 workshop on challenges in representation learning. It contains approximately 35,000 RGB images with size restricted to 48 by 48. The images were labeled with 7 basic emotion categories, which are anger, disgust, fear, happiness, neutral, sadness, and surprise. Google Image Search API was used to collect the images for dataset. The discussed expression has minimal number of images, that is 600, while other labels nearly have 5000 samples each. Most facial expression datasets have been created in artificial lab environments where people were asked to generate the required facial expression. Acted facial expression in the wild dataset has short video clips that contains spontaneous facial expression collected from movies. It has 7 basic expressions, the same as FER 2013 dataset. The dataset also captures natural facial expressions of people with nature head poses, diversity of race and gender. Many clips have multiple people in them, which can be used to train the algorithm to capture multiple facial expressions in one clip. The clip includes scenes with both indoor and outdoor backgrounds captured during day and night time to provide different lighting conditions. This can help researchers build algorithms that can generalize better. EmotionNet dataset contains 1 million images downloaded from internet which are taken in varying natural backgrounds and are labeled with 23 basic or compound emotion categories. The picture here demonstrates the characteristic of EmotionNet dataset. Let's quickly move on to know more about algorithms deployed in facial emotion recognition systems. Mainly, two types of algorithms are deployed here. First one is machine learning algorithm. It is an application of artificial intelligence that includes algorithms that pass data, learn from the data, and then apply what they have learned to make informed decisions. Second type of algorithm is deep learning algorithm. It is an evolved subfield of machine learning that structures algorithm in layers to create artificial neural network that can learn and make intelligent decisions on its own. In machine learning, mainly there are two types of algorithm. First one is supervised learning algorithms. These analyze the training data and produces inferred function which can then be used for mapping new examples. The second one is unsupervised learning algorithm. These are type of algorithms that learns patterns from untagged data. These exhibit self-organization that captures patterns as neuronal predictions or probability densities. But as datasets contained tagged data, we implement only supervised learning technique. Three algorithms implemented here are support vector machines, linear discriminant analysis, and hidden Markov models. A support vector machine is a supervised machine learning model that uses classification algorithms for two group classification problems. After giving an SVM model sets of labeled training data for each category, we are able to categorize new text. The basics of support vector machines and how it works are best understood with a simple example. Let's imagine we have two tags, blue and green, and our data has two features, x and y. We want a classifier that, given a pair of x and y coordinates, output if it's either blue or green. We plot our already labeled training data on a plane. A support vector machine takes these data points and outputs the hyperplane that best separates the tags. This line is the decision boundary. Anything that falls to one side of it will classify as green and anything that falls to the other as blue. But what exactly is the best hyperplane? For SVM, it's the one that maximizes the margin from both tags. In other words, hyperplane whose distance to the nearest element of each tag is the largest. A SVM introduced in 1992 is found to be theoretically and mathematically simpler than artificial neural networks. SVM maximizes the margin between the training patterns and decision boundary, thus tuning the capacity of classification function. For automated real-time facial expression recognition, the input data being from a video stream, we can employ an automatic facial feature tracker which performs the face localization and extracts 22 feature points. This model can then be used to dynamically classify unseen feature points and return the results to the user. Optimization of the parameters can be explained using the following tuning parameters: regularization, gamma, and margin parameters. The first tuning parameter is regularization. Regularization refers to the margin of hyperplane and how much do we want to misclassify each point in the training set. A high regularization parameter tends to classify all the training points correctly. A low regularization parameter tends to misclassify some points in the data, as shown in this figure. The second tuning parameter is gamma parameter. The gamma parameter decides the distance of the training points from a separating hyperplane. A low gamma means points far away from the separating hyperplane are considered. and a high gamma parameter means only the nearby points are considered. It is illustrated in this figure. The third tuning parameter is margin parameter. All SVMs try to achieve a good margin. Margin is a line separating two classes of defined data points. A good margin is as far as possible from both sets of data points. Thus, it makes sense that the margin be equidistant from both sets of points, as shown in the figure. The process of giving a result output emotion by using SVM can be done in the following method. There are three core steps involved: face detection in an image, facial data extraction, and classification of facial emotion. For a real-time video stream, localization is required for detection of human face, after which we crop and grayscale the image and finally resize it into a 48 by 48 pixel size as an input to our algorithm. For real-time automated facial expression recognition using SVM, we initially have a training face dataset like the FER 2013 along with the real-time video capturing device like a webcam or a video camera. We get our input image by capturing frames from our webcam. The first step involves the detection of the human face inside the capture frame. This image is then vectorized. Meanwhile, SVM gets trained on the training data shown in the second block, and thus the training model is ready. This model can now be used to classify images and test out results. We test this model out on an image not in the training dataset and display its output. The next supervised learning algorithm deployed here is linear discriminant analysis. Linear discriminant analysis is a dimensionality reduction technique. It reduces number of dimensions in dataset while retaining as much information as possible. For more than two classes, linear discrimination analysis is the preferred linear classification technique. LDA makes use of the Bayes theorem and makes the prediction by estimating the probability of a set of inputs belonging to each class. LDA are more optimized when the class distributions are Gaussian, but in non-Gaussian distributions, SVMs outperform LDA. For real-time face detection on the DFAT504 dataset using linear discriminant analysis, the results are significantly lower than SVM. The performance can be improved by adjusting the threshold value for each emotion, but even with threshold adjustment, SVMs outperform LDA. The next algorithm used is hidden Markov models. A Markov chain is a set of states of a system linked together used in a real-world computer simulations. For a given Markov chain, we can get the probabilistic simulation of the next state. Using a hidden Markov model, we can predict the set of unknown variables from a set of known variables. It can give us the probabilities of a state transition. HMM gives this probability based only on the current state the model is in and does not consider the previous state. Facial animation parameters describe the face shape and its movements. FAPs that control eyebrow and mouth movements contain a lot of information about facial expressions. We can build our Markov models on our defined FAPs to classify them based on 6 facial expressions. FAPs are extracted from the video and passed to HMM based FER system and facial expression is recognized. Moving on to the next slide, we have deep learning algorithms. Here, convolution neural network algorithm is implemented. This figure illustrates the working of convolution neural network algorithm. In deep learning, convolution neural network is a class of deep neural network most commonly applied to analyze visual imagery. They are also known as shift invariant or space invariant artificial neural network. CNNs are regularized versions of multi-layer perceptrons. This usually means that it is fully connected network. CNNs use relatively little pre-processing compared to other image classification algorithms. This means that this network learns to optimize the filters through automated learning. This independence from prior knowledge and less human intervention in feature extraction is a major advantage. Now we will have glimpses of various FER systems based on deep CNN algorithm. The first one is AlexNet on ImageNet dataset. AlexNet based on deep convolution neural network algorithm on ImageNet IL-SVRC dataset and achieved a top 5 error rate of 15.3% and won the ImageNet IL-SVRC 2012 competition. This made DCNN popular for the task of image classification. AlexNet has over 60 million parameters. It has 5 convolution layers and 3 fully connected layers, so in total of 8 layers. The convolution layer was followed by rectified linear units to add non-linearity and max pooling layer to reduce the number of parameters and helps deal with overfitting. The fully connected layers are followed by dropout layers. Dropout is a technique in which few neurons are randomly set to 0. In AlexNet, the dropout coefficient is 0.5. That is, output of the neuron is set to 0 with a probability of 0.5. Dropout reduces overfitting and co-adaptation of neurons. They use data augmentation, which artificially enlarges the dataset. The second system which applied DCNN algorithm was VGGNet on ILSVRC dataset. The input to VGG based convolution neural network is a 224 by 224 RGB image. Pre-processing layer takes the RGB image with pixel values in the range of 0 to 255 and subtract the mean image value, which is calculated over the entire ImageNet training set. The input images after pre-processing are passed through these weight layers. The training images are passed through a stack of convolution layers. There are a total of 13 convolution layers and 3 fully connected layers in VGG16 architecture. The VGG has smaller filters 3 by 3 with more depth instead of having large filters. It has ended up having the same effective receptive field as if you only have one 7 by 7 convolution layers. Another variation of VGGNet has 19 weight layers consisting of 16 convolution layers with 3 fully connected layers and same 5 pooling layers. In both variation of VGGNet, there consists of 2 fully connected layers with 4096 channels, each of which is followed by another fully connected layer with 1000 channels to predict 1000 labels. Last fully connected layer uses softmax layer for classification purpose. The network was able to learn more complex features due to the increased depth and brought down the top 5 error rate in IL-SVRC dataset to about 7%. It has over 130 million parameters and about 90% of those is due to fully connected layers. The third system is GoogleNet on ILSVRC14 dataset. GoogleNet is a type of convolution neural network based on the inception architecture. It utilizes inception modules which allow the network to choose between multiple convolution filter sizes in each block. An inception network stacks these modules on top of each other with occasional max pooling layers with stride to have resolution of the grid. It has 22 layer neural network and it won the ImageNet competition in 2014. It uses 12x fewer parameters than AlexNet. It achieved this by omitting the fully connected layers. The authors wanted to create a network that uses fewer computational resources while providing high accuracy because it would reduce power and memory consumption and can be used for many practical purposes. The next system we are reviewing is ResNet based on ImageNet dataset. The ResNet has 152 layers, 8 times deeper than VGGNet, and managed to achieve 3.57% top 5 error on ImageNet dataset. The authors found that when they increased the number of layers by adding convolution layers, the accuracy did not reduce, and instead, it got saturated because the network became too complex and it was hard to optimize using backpropagation. So the author introduced ResNet blocks given in the figure, which h of x is equal to f of x plus x, in which an identity function is added, which turns out to be a shortcut during the optimization of the network. This allowed them to add a lot of layers to the network, which would allow it to learn complex features. The network also performs well in the task of object detection and image segmentation, in which complex features are very helpful. This is a static image based facial emotion recognition system. Here the authors first detected the face from an image. The dataset contains labeled movie images. There is a lot of background noise, so it is important to first detect the face and then it was fed to Deep CNN to find the emotions. To detect the face, an ensemble of face recognition algorithm was used as shown in the figure. The ensemble consists of joint cascade detection and alignment detector, the deep CNN based detector, and mixture of trees. The network is first pre-trained on FER dataset and then fine-tuned on SFEW dataset. The deep CNN architecture used to detect the emotion is shown in this figure. It takes in 48 by 48 dimensional grayscale image as its input and have 5 convolution layers, 3 stochastic pooling layers and 3 fully connected layers. Stochastic pooling layer is used instead of a max pooling layer because it gives better accuracy when there is less training data. Max pooling chooses the maximum value, whereas stochastic pooling randomly selects the value based on probability distribution obtained by normalizing the values, which add randomness, thereby improving the network's performance. Fully connected layers contain dropout, which is also a mechanism for randomization. This statistical randomness improves the network's generalization and reduces the risk of overfitting. Random permutation to input faces is used which generates additional unseen training samples and improves the network performance. Now we will move on to real-time CNN for emotion classification. Here, the authors implemented a convolution neural network in a real time in a robot platform which has limited hardware capabilities for emotion and gender classification. They proposed two CNN models. Both models were designed to provide the accuracy to size ratio. The first model is a fully convolution neural network and does not contain fully connected networks. It is composed of 9 convolution layers, uses rectified linear units as the activation function, patch normalization is used to speed up the learning process, and global average pooling is used before the softmax layer. This model contains approximately 600,000 parameters. It did not have any fully connected layers because they contain a lot of parameters and increase the size of the model. The last convolution layer has to replace the fully connected layers, so the same number of feature maps as the number of classes. This followed by an average pooling layer which further reduces the number of parameters. The final layer is a softmax layer which to give the output prediction. Moving on to the second model and also the last model in our presentation, it is based on exception architecture. This architecture uses residual modules and depth-wise separable convolutions. Depth-wise separable convolutions contain depth-wise convolutions and point-wise convolutions. It is shown in this figure. Depth-wise convolutions contain d by d filter which is applied to each input channel separately, and pointwise convolution contains 1 by 1 convolutions which reduces the number of channels from m to n. This is done to reduce the number of parameters of the deep CNN. The final architecture is fully convolutional neural network that contains 4 residual depthwise separable convolutions along with batch normalizations and uses rectified linear units as activation function. They got an accuracy of 96% IMDb gender dataset and 66% on the FER 2013 emotion dataset. They used guided gradient backpropagation to visualize the features learned by CNN. Throughout this seminar, we have learnt various details regarding facial emotion recognition systems. Initially, we understood about emotions and importance of non-verbal form of communication. Later, we realized the value of facial expressions in non-verbal form of communication. We then hovered over various datasets that are used in facial emotion recognition systems. We also encountered different types of machine learning and deep learning algorithms and also various applications of it. Thus, we conclude that images in dataset need to be taken from natural environment so that they close the environment the algorithm is deployed in. We need to gather more training examples for less common emotions like disgust. The deep learning algorithm CNN outperform machine learning algorithms such as SVM. The pipeline of first performing face detection and training CNN to its output performs well. I would like to thank all the authors of various papers and also my seminar guide Professor Syed Noorian and all our faculties at Anjuman Institute of Technology and Management for their valuable inputs. Thank you.